Hello and welcome to another tutorial. Today we are looking at a skewed plate girder bridge on which we are conducting an influence analysis together with a moving load analysis. The bridge that we are going to model is really this one. This is the steel superstructure only, and we've seen this bridge before in a previous tutorial. It has skewed supports on both ends and it's got a lean-on bracing system here where we've got full cross frames with the diagonals, and we also have lean-on braces with just the bottom and top chords. If you are not familiar with lean-on bracing, this is a way to provide just enough system brace stiffness in order not to attract too much load in the cross frames in order to keep their sizes to reasonable dimensions. And there's other benefits like faster construction, reduced cost, easier inspection. There's tons of advantages to using lean-on bracing, especially for skewed bridges. As we've seen this bridge before, I'm going to go really quickly here on the modeling of the steel geometry. The deck elevation, which is the distance between the midplane of the deck and the bottom flange, is taken equal to 66 inches. This is something you can find just looking at your plate girder elevation and your deck thickness. These are the material properties for the steel and the concrete. You can see we're using the full E sub C for the concrete as we are applying live loads. 7 stiffeners along the bridge on to which we are attaching cross frames. And again, you can see ones and zeros here. 1 stands for full cross frame and 0 for a lean-on cross frame. Note that we're applying a multiplier of 65% on the stiffness of the cross frames. This is to account for the connection eccentricity, as that eccentricity induces a partial loss of stiffness in the members. This is now a provision which is into AASHTO. Just one segment to model the deck, as the bridge is pretty short and simple. 5 special fixities. You can go to the previous tutorial to find out more about these. We are just restraining here all 3 displacements on abutment 1 for girder number 1 at location number 2. That means at the bottom flange node, and just applying vertical supports for girders 2, 3, and 4. So we are letting the bridge breathe in a way. I will not click on this button here as the model is already run, but again, as I keep saying in every tutorial, if this is the first time you come across this form, please click on it, and same if you modify any of the reference points. This is in order to have subroutines for the mesh properly define the right geometry for the bridge. We have a mesh size of 3 feet, which is pretty coarse, but as we're doing an influence analysis, which is a pretty brute force method, it is advised to use a rather coarse mesh. 1 cross-sectional profile here that we are assigning to all the segments, of course. And here comes the interesting part. We are looking at 8 influence surfaces that we want to derive. And so here we have the first 4 will be, and let's go back to this figure. We're looking at the design forces for these 4 members, then these 2 members, and finally these 2 members. So that's 8 overall. And you can see here we have first diagonals, then bottom and top chord, and then bottom and top, bottom and top. This is why here we have, and let's go back to the form where we have defined the cross frames for you to really understand. The cross frames are located on bay number 1 at 24 feet from the abutment. That's why we have 24 here. And we're looking at desired quantities number 11, 12, 13, and 14, which is really cross frame diagonal 1 axial force, the other diagonal force, lower chord force, upper chord force. Okay. And because this is not anywhere on the cross section, the program will automatically gray out these cells and enter a 5 by convention. This is the 5 here is just a convention. The next 2 influence surfaces are for bay number 2 at 17.3 feet from the abutment. We're looking at the bottom chord and top chord forces. And then finally, the last 2 influence surfaces are for bay number 3 at 10.7 feet from the abutment. bottom chord, and top chord forces. This is the form where we define the moving load analysis, all the required parameters. We have one truck model on which we have 3 axles, and the distance between the wheels is 6 feet. Here are the left and right wheel loads, spacing between the axles, and yeah, this is pretty much all we need. We have a presence factor of 1 here because it's a fatigue analysis. For the design lane, we're taking the width equal to 34 feet. This is because the bridge is 36 foot wide, okay? 3 times 10, where 10 is the girder spacing, plus 2 times 3 for the overhangs. And then, so we're saying really that we have 1 foot on either side of the bridge where we're saying that we won't have any truck. We are centering the design lane over the bridge width. So because the bridge is 36 foot wide, the center line of the design lane is at 18 feet. Then we are saying here on this form that we are in effect conducting live load analysis for the 8 influence surfaces. And here there's a slight bug where this check button is not checked when we open the form, where in reality it was checked when the program was run. This is something that will be fixed as soon as possible. We have here 61 truck positions along the width of the design lane, and this is because, again, we want something rather fine for the moving load optimization. So it will really mean that there will be 61 different lateral positions that will be checked. And in the longitudinal direction, we'll have an increment of 0.5 feet. We can run the model, but really this will take about 7 to 8 minutes because we're applying a unit point load everywhere on the deck, and then building the influence surface. We have to do that many times because there's many nodes, and then the solver, another subroutine, will find the critical vehicle load positions. So instead, let's just go to the results. We can see our bridge with the deck explicitly modeled, and the interesting bit here is to check this radio button, and this is influence surface number 1. So that will be the diagonal, the force in the diagonal here on that cross frame, the second cross frame from the abutment. And we can click on this button to look at the critical load position. This view is slightly confusing, so let's go instead to a top view. You can see that, as expected, we left 1 foot free from the edge of the deck, so it makes total sense for the subroutine, for the program, to find a critical load position that's here. This will be the 3rd axle, this will be the head of the truck, and this is the critical position here for that diagonal. So looking at the influence surface, the program finds that the maximum force range that this diagonal will experience is equal to 3.1 kip. Okay. We can look at influence surface number 2 and look here. So that's the other diagonal, and here the maximum range would be 6.17. Here you can see it's all blue, so the minimum force would be negative, so that's compression, and this critical load position would lead to a value, to force in the diagonal of minus 6.2 kips, so compression force. We can go to influence surface number 3, which would be the bottom chord, influence surface number 4, and you can see here that the position for the maximum value and minimum value are aligned. Okay, this is really specific to fatigue analysis. This is quite important. We're not allowing the truck to move laterally here. The maximum range has to be obtained for 2 truck configurations which are in the same lateral position. Then we can go to influence surface number 5, number 6, number 7, and number 8. And here again, the maximum range will be the design force range for its of these chord members. So this is pretty interesting. We believe this is pretty useful to have 3D shell models in order to find the design cross-frame forces for fatigue analysis. If you have any questions, just write a comment or send an email. Thank you very much.